Hello and welcome. This is going to be our lecture video for December 10th. Let's go ahead and get started. Our goal today is to be able to find roots of a polynomial using rational root theorem and conjugate root theorem. Why are we doing this? These theorems help restrict the possible solutions for the roots of a polynomial and make them easier to find. Let's start with the rational root theorem. Have a version of this copied down into your notes, but here's like a very formal way of writing it out. Rational roots must have the form p over q, where p is an integer factor of the last constant term, and q is an integer factor of the first term's coefficient. Notice we say integer here, which means that negatives are allowed. What are the possible rational roots of this here cubic? So what first thing I'll do is factor my leading coefficient and my constant, 1 and 5 here, 1 and 2 there. Then I'll make every fraction possible with last over first. 1 over 1 is just a 1. 5 over 1 is just a 5. 1 over 2 is a 1/2. 5 over 2 is a 5/2. And then I need to get the negative versions of all these numbers. So -1, -5, -1/2, and -5/2. All right. If this function has any rational roots, it will be in this list here. And because the biggest exponent is odd, we are guaranteed 1. All right, so if it's odd, there must be at least 1. So 8 numbers is still a lot to check, but it's a lot fewer than if we were just picking numbers at random. And how we check them is with synthetic division. All right, let's try this again. Here's our next polynomial. Go ahead, copy it down. The factors of the leading coefficient are 1 and 2, and the factors of our constant at the end are 1, 2, 3, and 6. Those are all the numbers they'll divide into 6 evenly. Let's make all the fractions possible with last over first. So 1 over 1 is 1, 2 over 1 is 2, 3 over 1 is 3, 6 over 1 is 6. And now we have to do them all over 2. So we get 1/2. Then we get 2 over 2, but that's a 1, which is already in our list. So we move on. 3 over 2, and then 6 over 2, which becomes a 3. Again, it's already in our list. And then we just have to do the negatives of all of these numbers. And we have a total here of 12 possible rational roots. Because this is odd, we're guaranteed at least one of these will work. So sometimes I call this our search area. All right, and we're going to start using synthetic division. Let's try the easy ones first. We'll try 1 against this function. So drop down the 2, we get a 2 here, -3, -3, -4. This one's not going to work. I can already tell this. We're not going to get a 0 here. All right, so we move on to +2. So 2, -5, -1, 6. I'll put a 2 here. I drop down the 2, -4, -1, -2, -3, -6, 0. So I did get a 0, meaning that 2 is a rational root. Now, it might be the only one, but there could be up to 2 more in this list because of the fundamental theorem of algebra, which states we will have 3 solutions. But we won't keep checking them because now we've got this down to a quadratic, 2x squared minus x minus 3. And we can solve this with a variety of methods. I'll just do factoring by grouping. So combine the 2 and the -3 to become a -6. Split that -6 into 2 numbers that add up to a -1, which would just be 2 and -3 again. So we'll split that middle term into a 2x minus 3x, 2x squared plus 2x minus 3x minus 3. Group together the first 2 and the last 2 terms, and pull out the greatest common factor, which is a 2x from the first one, leaving behind an x plus 1, and a -3, leaving behind an x plus 1. Regroup And we get 2x minus 3 times x plus 1. All right, by factor theorem, we can say that x equals -1 is one of our remaining roots, and then we should use the ZPP on this factor to get that 2x minus 3 equals 0, plus 3 plus 3. 2x equals 3, divided by 2, divided by 2. X equals 3 halves. And then let's bring this down here so all our answers are near each other. X equals 2. And there's all three of our answers. If we go back up to our search area, you will see all of them were in the search area, -1 and 3 halves, which means it can't be any of these other ones because we were only allowed 3. So I'll cross them all out. Okay, conjugate root theorem. If A plus BI is a root, A minus BI is a root as well. Complex roots always come in pairs, and those pairs are always conjugates of one another. All right, this works for just irrational solutions as well. If we have A plus the square root of B, that implies A minus the square root of B as well. And you don't have to have an A value. If you just have BI, that implies -BI. And if you just have square root of B, that implies negative root B. All right, so if the square root of 2 and 1 plus I are roots of some polynomial p of x, what are two more roots? Well, just take the conjugate of each of them. When it's just a monomial like the square root of 2, then it's negative square root of 2. Complex number like this, find its true conjugate by flipping the middle operator. All right, so you get these two roots given to you, you get two more for free. It's the buy one, get one free theorem of mathematics. All right, and so the conjugate root theorem leads us to problems like this. Find all roots, one root has been given. Well, if one root has been given, but it's an irrational root, then really two roots have been given because the next one is so easy to find. You just flip that middle operator, and we get this one for free. Now by factor theorem, we can turn these roots back into factors by just subtracting them from x. I'm going to do that right here. So x minus -2 plus root 19 and x minus -2 minus root 19. Notice I have it set up so now I'm multiplying these two factors. Factors can be taken out of polynomials. They can also be put back together. With conjugate factors, it's good to put them back together to create a simple quadratic factor that represents both of these. In order to do that, I just have to multiply them. We'll start by distributing in this negative here and here. And I'll get x plus 2 minus root 19 times x plus 2 plus root 19. All right, and now let's distribute this. That requires we do first to first, first to second, first to third, second to first, second to second, second to third, third to first, third to second, third to third. You can get all of the combinations possible. There's going to be 9 combinations there. So I get an x squared plus 2x plus root 19x plus 2x plus 4 plus 2 root 19 minus root 19x, always putting the x at the end when you multiply a number in x, minus 2 root 19, and then negative root 19 times positive root 19 is the same as negative root 19 squared, and the square roots cancel out, so it's just a minus 19. All right, because these were conjugates, a lot of canceling happens here. In fact, everywhere we see a root 19, it's going to cancel. All right, combine your like terms, and we get this quadratic factor, x squared plus 4x minus 15. All right, this is a guaranteed quadratic factor of this quintic, so it should be able to divide out evenly. Let's set up our long division next. So big quintic goes underneath the long division symbol, x to the fifth minus 27x to the third. No quartic term, that's interesting. Plus 60x squared minus 124x plus 240 divided by x squared plus 4x minus 15. All right, my tips on the long division is just focus on the biggest factors and all the other numbers sort of come along for the ride. So x squared times an x cubed equals x to the fifth. We get an x to the fifth plus 4x to the fourth minus 15x cubed. And we want to subtract this away. These terms cancel. There's no x to the fourth up here, so that we're just going to get a minus 4x to the fourth down here. And negative 27 minus a negative 15 is the same as negative 27 plus 15. We get a negative 12x cubed. And we'll drop down at least one more term, plus 60x squared. Next up, we're going to have a minus 2x squared up here. And now multiply that in, we get a not a minus 2x, it's going to be a minus 4x. For some reason I was seeing a 2 for it to combine with. So minus 4x, we get a negative 4x to the fourth minus 16x cubed plus 60x squared. Subtract this away. And we get negative 12 plus 16 is going to be a 4x cubed. These terms cancel out as well, so I'll drop down our minus 124x and keep going. X squared times a positive 4x is going to give us a 4x cubed. So now we get our 4x cubed plus 16x squared minus 60x. Subtract this away. There's no x squared there, so we're going to get a negative 16x squared. This is really negative 124 plus 60. It's going to become a negative 64x, and we'll drop down the 240. And our last term is a minus 16. Let's make sure that gets us these terms back. I'm pretty sure it does. So it's good at the bottom here to show that we get a zero remainder, although we already have our answer up at the top of x cubed minus 4x squared plus 4x minus 16. All right, so we've simplified our quintic down to this cubic. Looking at this, we could maybe factor it by guess and check. You'd have to have an x squared and an x, and then two numbers that multiply to be negative 16. Then you got to make sure they add to be these. I actually don't think that that's too bad. Let's try it. So I'm going to try to do simple factoring with an x squared here and an x here. The constants have to multiply to be a negative 16. But one of them is going to come over and form this x squared term, and it's going to be a minus 4. One's going to come over and form this x term. The only way to do that is with a positive 4. So I'm pretty sure this factors into this, and we can just double check by foiling this. We get an x cubed back, then we get a minus 4x squared, then we get a 4x, then we get a minus 16. So this was just by guess and check, and this one happened to work out really well. If not, we would have been doing rational root theorem, and hopefully we would have guessed positive 4 here pretty quick. But that was guess and check. And now we can use the ZPP To finish solving this, x squared plus 4 equals 0, minus 4, x squared equals -4, square root, x equals plus or minus 2i. And then over here, we just get x equals 4 by factor theorem. So this was a quintic by the fundamental theorem of algebra. We were expecting 5 answers. Did we get them? 1, 2, 3, 4, 5. All the answers, only one of them was rational. 2 were irrational, 2 were complex. All right. So we'll call that good for this video. I'll embed a few more for you to try right here. And have a good rest of your day.